the last thing we will do is we will negate the well-defined property. So, to negate the well-defined property, let's go back and state the well-defined property. The definition is for all a, b, y, z, and s, if both a equals y and b equals z, then a star b equals y star z, provided that either of these two expressions are defined. Now, so let's negate this. This will be a little bit harder work from foundations, but when we negate, the negation of star is well defined on S would be star isn't well defined on S. That part's not hard to negate. Star is not well defined on S. Now, remember we have a for all statement here for all a, b, y, z, and s. So we need to negate this. So there exists an a, b, y, z, and s such that, and now we have to negate the predicate, which is if both a equals y and b equals z, then a star b equals y star z. So when you negate an if-then statement, remember from foundations in section 1.4 in foundations that it's both the if part and the negation of the then part. So the negation will be there exists a, b, y, z, and s such that all of the if part, so a equals y, b equals z, and the negation of the then part. So a star b does not equal y star z. So star is not well defined on S means there exists an a, b, y, z, and s such that all of a equals y, b equals z, and a star b does not equal y star z. Now, this is a fancy way of saying that a star b can equal two different things. Either a star b if you look at a star b directly, or y star z, which is different if you sub in y for a and z for b. So you might ask, if all four of our familiar operations, addition, subtraction, multiplication, and division, are well defined, is there any operation that isn't well defined? Why do we care about this if everything we're familiar with is well defined? Well, it would be wrong to just assume that any operation that you write down is automatically well defined. Here is an example of an operation that is not well defined. You all know that when you're adding fractions from middle school, to add fractions, you have to get a common denominator. But let's just look at the operation for the wrong way to add fractions. So we'll define star, the operation star be the wrong way to add fractions. In other words, m over n star s over t is adding across the tops and adding across the bottoms. So m plus s over n plus t. How you don't add fractions, but how you would add fractions if you didn't understand how to add fractions. Now, of course, it is correct to multiply across the tops and multiply across the bottoms when you're multiplying, but when you're adding, of course, you have to get a common denominator. But let's look at its own right, the operation of combining two fractions by adding their tops and adding their bottoms. And our claim here is that this operation star is not well defined on the set of rational numbers. This star is not well defined on Q, the set of rational numbers. So let's see. We want to apply the definition of not well defined to the operation star, which is now wrong addition, to the set Q. So we want to show that there exist rational numbers A, B, Y, Z in the set Q such that all of A equals Y, B equals Z, and A star B does not equal Y star Z. So we are going to pick, because we're proving a statement with an exists quantifier, we are going to pick 4 rational numbers. But we just can't pick any old rational numbers. We have to be a little bit careful because the A and the Y we pick have to equal each other, and the B and the Z that we pick have to equal each other. So let's choose A equals 1/2, B equals 1/3, and now let's choose a Y that is equal to 1/2, but looks different. So Y equals, let's do 2/4. And let's choose a Z that is equal to B, so equal to 1/3, but looks different. Let's choose Z equal to 3/9. Now, we had an exist quantifier, so we chose them. Now we just have to argue that A equals Y, that B equals Z, and that A star B does not equal Y star Z. So since 1/2 equals 2/4, it follows that A equals Y. Since 1/3 equals 3/9, it follows that B equals Z. Remember, to show that A star B doesn't equal Y star Z, we have to calculate each side separately. So consider the following calculations. Now, A star B here is going to be 1/2 star 1/3. Remember, the way we defined this operation is to add the tops and add the bottoms. So 1 plus 1 over 2 plus 3, or 2/5. However, Y star Z Again, this time is going to be 2/4 star 3/9. So again, if we add the tops over, add the bottoms, 2 plus 3 over 4 plus 9 equals 5 over 13. And notice that 2/5 does not equal 5/13. So therefore, since 2/5 does not equal 5/13, we may conclude that A star B does not equal Y star Z. And that ends our proof. Some things to keep in mind here are that you need to know the definitions, because the definitions tell you how to write the proofs. Knowing what it means for an operation not to be well defined tells you what you need to do to prove an operation is not well defined. You need to choose A, B, Y, Z, and Q. You need to argue that the A that you chose equals the Y that you chose. The B that you chose equals the Z that you chose. Then you need to calculate A star B and Y star Z and argue that they aren't equal to each other. The definition provides a roadmap for being able to write the proof. Now, what this says is we've all known this is the wrong way to add fractions, but this is actually not even a consistent way to combine fractions, because depending on what you use to equal a fraction, if you combine the fractions this way, you could get two different things. Okay,